How are we all? Third week. You alright? Feeling drained yet? Feeling used to it? I don't know. This week's feeling smoother than me. I feel like I'm getting somewhat used to the days, but we'll see if that improves or worsens. Alright, so we are at the prophesied time of 4:30. So, I'm on web courses because, at the beginning of every class, do some logistics and stuff like that. So, we just had our first quiz end. Yes. Our first one just ended this last Saturday. So I sent out an announcement. Remember, the quizzes, ultimately, so they're basically the homeworks. They're basically my graded homeworks for this class. They're set up in a way so that if you put in the effort, you put in the time, you should do well on them. So to that end, they are designed to be able to give you all kind of a sense of how you're doing. So to that end, if you got a 4 or a 5 out of 5, so it's out of 5 points. If you got a 4 or 5, 4 questions right, 5 questions right, that means you're doing well. That's kind of your indication that things are going smoothly for you. If you have 3 points or below, that means that was a weaker section for you. And if that is happening consistently, that is an indication not that you are a failure, but that you may need to you may need to change your strategies. You may need to go to office hours or the help room hours that I mentioned. If I hear from SARC, maybe go into SARC, maybe find some people to work with. It just indicates that you're not learning the content at the level we need to. That does not mean you're stupid. That just means you need to change your study strategies. That's all that means. If you're not succeeding at something, do not take that as a failure. Physics is hard, y'all, for a lot of people. I teach a physics class with engineering students. It's going to be hard for them as well. Physics is a challenging topic, and so if you're struggling with it, don't stay there. Use that as an indication. It didn't go well. Change your strategies. Talk to me. If you're not doing the problem sets, start making sure you're doing those problem sets. Make sure you spend the time to understand them. And as the class goes on, again, I'll kind of point out strategies to be successful and how to approach problems and all that stuff. But that's kind of a flag for you all. Each week's quiz is an indication, do you understand it? Okay? Now, my assumption is when saying that grade-wise, how you approach the quizzes is going to basically directly align with how much you're going to benefit from the quizzes. If someone else does the quizzes for you, if you look up the answers and just follow a solution online to do that, sure, you'll get the quiz points. But half the grade in this class is the test, and I can guarantee you if that's a strategy used for every quiz and you're not kind of getting that feedback of do I understand it, the test is going to come along and you're not going to have those things. You're not going to have someone else to do it for you. You're not going to have the solutions online. So, just keep that in mind. The test will not go well. So use these quizzes for what they're worth. Go into that first quiz attempt, honest, be prepared for it, do the best you can. If you run into problems and questions and stuff like that, check around. You can come to my office hours and ask me questions about the quizzes. These are effectively homeworks. You can send me emails about it. That's again why I recommended you all do not wait until Friday evening to do the quizzes, because remember, I do not respond to emails over the weekend. I will on Monday. The quiz is closed by that point and I can't do much for you. So, anyway, just mentioning that, I have not looked at the grades exact, so this is not me calling out anyone. This is just me saying, hey, this is how to be successful. I want you all to be successful. This is why they're designed the way they are. Please take advantage of them. And again, if you're doing awesome. That's a great sign. If you're not, that's okay. Just make some changes. Talk to me. Let's get through this together. It's only the first quiz, so I'm saying it sooner than later so we can make certain we're getting those good strategies sooner than later. Now, to that end, to help you all in understanding how to do these, if it didn't go smoothly, or even if it did and you're uncertain on stuff, every week I post the solutions to the quizzes. So I sent out an announcement about that. If you go to the week 1 tab, Quizlet solutions are right here. Now remember, there's different versions of each problem, so maybe a number will be different, but they should look very similar to yours. Again, maybe one number is different, but physics is not about sure, at the end of the day, there's a number to answer, but it's the process that matters. And so, if you have a different number, that's a great opportunity to figure out how that different number maybe changes things in this problem. So they're worked out. If it's a step 1, 2, 3, 4, I generally write out steps 1, 2, 3, 4. I solve it the way that I show the steps and all that stuff as well. So check that out. It's a resource. It's available. All right. Okay. Any questions about the quiz or anything with those being first one done? All right, cool. As this semester goes on, we're going to get more and more comfortable with it. The beginning is always hard because every class is different, how it's structured is different. So something I also want to do is I always like to give a quick recap of what we did last class, just because, again, I know after an hour, 20 minutes, it can be hard to figure out. So last week, we talked about electric fields, this thing that exists that makes forces. And I started last class with this weird thing called flux. It's a reminder, flux is just how many field lines, these electric field lines, how many pass through the surface. So we gave the equation for that. It depended on the angle, it depended on the area, it depended on the strength of the field. But conceptually, it's just kind of how many of these arrows, how many of these electric field lines pass through it. So there's our equation with the angle. And we kind of discovered this. I talked about the normal vector, where if you want the normal vector, you just take a pencil or something, put the eraser flat down, that's the direction of the area. So when we're talking about the angle, it's the angle with respect to the area and the field. And we said that when these things are parallel, you get the maximum flux. The math shows us that, but conceptually, the number of arrows going through it is also maximum. So we also see that there. Whereas when they are perpendicular, if my electric field and my area are perpendicular, none of those arrows are passing through it. The angle is 0, or the angle is 90, cosine of 90 is 0. So we went through flux, did some stuff. We practiced some geometry. We had some technical problems with my computer. It was a good time. We introduced another way to calculate flux, which was the amount of charge enclosed. So we had one equation for it, then we had this one that's actually a little bit easier, which was literally just count how many charges, figure out the net charge inside, and that's all that matters. It does not matter what's outside of it. And we also introduced this variable epsilon naught. Epsilon naught is just a number, 8.854 times 10 to the minus 12. As you all use it, you'll get more comfortable with it. And then the last thing we talked about was we had 3 different symmetries. Let's see if I have one. I think I have one slide with all of them on here, somewhere up here. So we had 3 different symmetries. We had a rod of charge, we had a plane of charge, and we had a sphere of charge. And we said, hey, if you do some derivation involving Gauss's law and some calculus that we don't have access to, so I didn't go through derivation, we can find the electric field due to these 3 things. And that's really what you all needed to know, was the equations for these electric fields. And I kind of chucked those in at the end. We have a nice little slide somewhere here, I believe, that has the main points. Maybe not, I lied. All right, but we have those. So there's the line of charge, sigma over 2 pi epsilon naught r. We have the plane of charge. Sorry, this is the one sigma, that was lambda. Sigma over 2 epsilon naught. And then, again, these are just equations. So if you have a plane of charge and you want the electric field, use that equation. If you have a line of charge, you want the electric field, use this equation, sigma over 2 pi epsilon naught r. If you have a sphere of charge and you want the electric field, we had 2 equations, one if you're inside, one if you're outside. Okay. So that's kind of the quick recap of everything we did last time. That's the main things you need to know is how to get flux, how to get the electric field, and that's what a lot of the problem set's going to revolve around. Just calculating electric field, its vectors, calculating flux, and as you all go through these, the nature of physics is the only way to learn it is to do practice problems. I could stand up here for hours, and not only would it be miserable for you, it'd also be miserable for me. Listening to someone talk for hours does not do any good. The best way, really the only way to learn this, I stand up here, I talk, I give you the ideas, I give you the concepts. We do a little bit of conceptual understanding. Hopefully by the end of class you have a little bit of conceptual understanding. But really, especially the math, there's no way around it. You got to do the problems. My high school students, it's the same thing. Now, the beauty with high school is I can actually work. I have the time to give them problems and then work with them. And if you come to my office hours, that's what I'll do with you as well, is work with you kind of one-on-one and help you through those. If you go to the help room hours, same thing. But yeah, you just have to spend the time if you have not done that. So last week, we finished this stuff. And so yeah, quiz 2 is going to be due this Saturday. So if you haven't started the second chunk of problem set problems, you're going to want to do that sooner than later. You don't want to get backlogged, y'all. You do not want to have a because the reason I structure these the way I do is we finish the content. Then you kind of have a week to both learn the material, and then at the end of it, you assess yourself. And the next week, the cycle repeats, and the cycle repeats. It is scaffolded this way so that when you get to test time, you have gone through all the things. Now, you'll know you're behind if when you get to the quiz, you don't know how to do it for each week. This is not something that you can learn 5 weeks of content 1 week. I'm very thankful I'm not teaching the summer class of this because, oh my gosh, physics in summer. If you have not seen physics before and you try to take it during the summer, it is brutal because there is just not that time to process stuff. It's either you pick it up because your brain's good at it or it's a struggle because time is just an important part to be able to practice and all that kind of jazz. And we have that time, as much at least as they give us. So, anyway, that's my quick spiel on that. Any quick questions about what we did last week? Before I jump into this week. Okay. So we've talked about forces, we talked about charges, and then they interact, opposites attract, electrons repel. We said that what makes this stuff happen? We said, okay, there's these fields, and we kind of found the fields due to a bunch of things. Again, electric fields, you can think of them like gravitational fields. So now we're going to take the next step, another way of understanding why this happens, and that is to do with energy. Energy is something you learn in Physics 1. Energy takes a bunch of different forms. And so one of the rules of the universe is that everything wants to go to lower potential energy. Everything does. I mean, one of the reasons things fall, they want to go to lower potential energy. When you have atoms and you have electrons floating around them, one of the rules of quantum mechanics is they want to go from those higher energy levels to lower energy levels. The reason chemicals bond together is it gets them to a lower energy. So everything in the universe is another way of explaining it. And so when we have these charges, there's energy associated with these things. Energy is the ability to do work, basically to apply a force on something. And so we're going to see that today in the context of these types of problems. So let's jump right into it. So yeah, we're going to identify what the heck electrical potential is and electrical potential energy. And like all physics, we're going to use them to explain why things do what they do. And yeah, how we can actually use this electrical potential. I'll go ahead and give you all a spoiler. Another name for electrical potential is voltage. And that should be a word that you're familiar with. You've probably heard it's on your batteries. So this is where we start to get into some of the real world. The variables we see here are going to be variables that you interact with on a day-to-day. And most people have no idea what voltage is. Hopefully, you will know what voltage is within a week or two's time. And it's everywhere. It's on every battery. You plug stuff into a wall. There's voltage, all that jazz. Okay, so to that end, reminder to you all, clicker questions. The grade from last Thursday was our first kind of official clicker question points. Hopefully you've got your thing working. If not, we got to figure that out sooner than later so you don't miss out on these things. Oh, another benefit. So I've gotten a couple emails with this. I'll mention this with clickers and then I'll read this problem. So feel free to read. But if you are watching this remotely, YouTube has a latency to it. There's just streaming delay. That's how it goes. And to that end, if I'm streaming the class, there is going to be delay, even if I set it to lowest delay. So when I have these questions open only for a minute, maybe a minute and a half, if there's a 30-second delay, just take whatever time I give you all, and they're not going to see it till 30 seconds after that. So if you're online, keep that in mind. However, if you have the Clicker app thing, it will send the question to you instantly. There's no delay from when I send it. So even though the stream will be delayed, you'll actually get the question the instant I send it to you all in class as well. I've just gotten some concerns. I've heard some concerns where it's I was doing it remotely and it was only open for 5 seconds. On the stream it was open for 5 seconds and it closed. That's because there was a delay from the stream. There's a delay to the stream. And the reality is I just can't leave these questions open for twice the time to account for that. Again, I offer that as a service, but at the same time I don't cater. You all are my main emphasis, making certain I get through the steps. So anyway, let's read this problem. From Physics 2053, Physics 1, you drop a water balloon with mass 1 kilogram from the top of the physical sciences building. That's the one where my office hours are in. Hoping to smash a friend who walks by. Which value is the closest to the speed at which the balloon hits the ground? It's a good thing I gave you some time because there is some math to it. Why am I giving this problem? One, I am not going to ask you a problem like this in a quiz or a test. Okay? So just heads up. But there's a reason for the madness. The ideas that you learned in Physics 1, a lot of them are going to transfer. So really this question is saying, do you remember the idea of energy? This is an energy problem. That's the easiest way to solve it is with energy. Do you remember conservation of energy from Physics 1? And if you don't, that's okay. I'm going to teach you all, we're going to go through all the rigmarole. But if you do, awesome. It's going to make this that much easier for y'all. All right, so we'll go to 240. I think we got most people. And this is a more mathy problem than I generally give you all, but there's a reason for it. For clickers, at least. All right, and 5, 4, 3, 2, 1. All right, so let's start solving through this problem. So one of the things you hopefully learned at Physics 1, whether or not you remember it, that's, who's to say? But hopefully you at least learn, as we're solving through this, hopefully it at least seems memorable in some capacity. I would like for you to stay there. All right, so, what's our givens here? We got mass equals 1 kilogram. So this is that problem-solving process. What's given? We have our height of 10 meters. We do know gravity causes things to fall. Oh, and let me close that to speed things up a bit. Okay, and what are we solving for? We are solving for the velocity at the bottom. No, we don't know it yet, and it's definitely not 0. Okay, so one of the things you hopefully learn in Physics 1, conservation of energy. Energy you start with equals energy you end with. Energy is conserved. So what kind of energies do we have? So, energy initial. And this is kind of weird because E looks like electric field, but energy initial equals energy final. What energy do I start with? I start with potential energy. Potential energy, your instructor may or may not have used U. So we have potential energy plus kinetic energy. U is the variable for that. Again, you do not need to know this necessarily. We're going to see some of this later. So potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. If you're having flashbacks, hopefully they're good ones. So we look at this and we say, do I have potential energy to begin with? Yes, I'm above ground. Do I have kinetic energy to begin with? No, I'm not moving. So we're going to see that in a second, the equations, and they'll remind us of that. Do I have potential energy at the end? No, because I'm at the ground. And we remember that the equation for potential energy is mgh. We remember that the equation for kinetic energy is 1/2 mv squared. We will use 1/2 mv squared again. That's going to show up. Okay, and masses cancel, so you actually didn't need it. And you kind of rearrange, 9.8 times 10 equals 1/2 times VF squared. So if I just rearrange this, VF is going to be the square root of 2 times 9.8 times 10. All I did here is I multiplied that 1/2. 1/2, if you divide by 1/2, it's the same as multiplying by 2. And the opposite of square root. We plug that in the calculator, and we get 14. Great, fantastic. What a wonderful problem. Again, all I'm wanting you all to see here is conservation of energy. This is what I wanted to remind us of. The energy we start with is the energy we end with, because we're going to need that concept today when what the heck am I teaching you? Okay? So, energy I start with is energy I end with. Now, this energy, this potential energy was due to gravity, hence the G inside of it. As you lift things up, you increase their height, and they gain this gravitational potential energy. All right, this is another throwback. This is more of a conceptual one. In your Physics 1 class, hopefully they showed you that if you do the change in potential energy equals something. It's got a special name. Is it the spring constant? Is it the displacement? Is it acceleration? And is it work? What is the change in potential energy equals blank? This is a you know it or you don't situation, so we'll just go to a minute. And if you don't, that's fine. I'm going to teach it to you. I'm going to remind you. All right, we'll close this out in 5, 4, 3, 2, 1. So change in potential can be rewritten. So that delta, this is the delta sign, that stands for change. So change in potential energy is the work done. Okay. Now what is work? Well, we're also going to remind ourselves at some point that work is force times distance. That's kind of a simplification of it. Technically, it's cosine of the angle. But work is the transfer of energy. How much energy gets transferred is based on the change in potential, also change in kinetic. It relates to both of them. So this work, it's a change in energy of a system is kind of the way of thinking about it. So, how is work related? We just showed that, so I just kind of put those there, so I'm not going to write them again. But yeah, we need to remember these definitions. We need to remember that work, and technically it's the negative change in potential. And we're going to need to remember that work is the force distance cosine of theta, where theta is, again, we're going to see this in a bit, but this is stuff we've seen in Physics 1. This is from Physics 1, so this is not technically out of nowhere. If you forgot it, that's okay. We'll work through it. But hopefully this is looking somewhat familiar. It's all building to our class today and what the heck is going to come in. So again, this is just a picture showing this. We have force, we have a displacement, this delta R is displacement, and the angle is between them. I'm not going to even spend that long in the slide because this is just reminders. So the angle is the angle between force and the displacement, and the equation was work equals force, change in R, cosine theta. All right? We can divide things, doing integrals, not going to bother with that because that involves calculus. Okay. So this is finally connecting it to what we care about. So we learned last week that force is Q times E. That was an equation I gave you all. If you have a charge in an electric field, it experiences a force. So we then take our definition from Physics 1 that our change of potential energy equals work equals the negative change in potential energy. Work equals F dot D. If A equals B and B equals C, then A equals C. If both of these things are work, then they all equal each other. So we can set up this relationship. I literally just replaced, so bam, put that one there. That one went there. And we're just building this equation. It's just, whenever I show you all an equation, you don't need to know the derivation, but it's good to know it's coming from stuff I've taught you. It's all building. All right, and then we replace force with what we learned last week. Force is Q times E. Again, just building this. This is how physics is discovered, from bit by bit, Lego bit, block by block, building on each other. Buildings don't get built by going to the 10th story first. The first 9 have to get built. So, as we're taking those building blocks we've learned, and we get the change in energy equals Q times E times dot D. So long story short, potential energy of a charge, there's the equation for it. We just derived it in 3 lines. The change in potential energy of a charge, all you need to do to find it, take the charge, multiply that by the electric field, and again, we can kind of write this. This is a dot product with vectors, but for our case, these will always basically simplify to this. A dot product just gets that cosine of theta, okay? So the change of potential energy when we talk about, instead of talking about gravity, instead of talking about mass and gravitational potential, so instead of having mgh, now I have QED. The change in potential is QED. Okay? And we can actually draw parallels here. We can so charge is kind of like mass. So change in potential energy when it came to gravity was mg change in h. That was the equation that you all saw, way back. Potential energy is defined as mgh. So we can draw some parallels here. Q is kind of like m. The distance is kind of like h, and we're going to see it a bit clearer when instead of having change, when we actually have the value. But we can start to see that there's some parallels, even though these two things have electric fields and gravitational fields are not connected in any way that we understand, we do see some parallels, which is kind of cool. Okay, so again, as right now it's the derivations part, it's probably not most fun, but as we start to get to the equation, hopefully it'll be more clear. So an electron is released from rest a distance z above a positively charged infinite plane. What is the speed of the electron right before it hits the surface? Okay, so this will let us use that equation, and that's going to help it hopefully make a bit more sense. It's kind of like if you've seen a construction tool and you had no idea what it was for, and someone said, here's this thing. It makes a lot more sense when you see it in use. All right, so how are we going to solve this? It's this problem is just like dropping a water balloon off the building. You're like, how is it that? So I'm going to start with some potential energy due to the electric field specifically, plus kinetic energy initial equals potential energy final plus kinetic energy final. Okay, so just like the setup we did before, potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Same thing, but now the energy is coming from something else. It's coming from this electric field. So first thing we can do, the electron is released from rest, so I have no kinetic energy to begin with. Kinetic energy is due to movement. So that term flies away. And then what I can see here, if I subtract that potential energy final to this side, and if I pull out a negative, again, just to make this as clear, if I pull out a negative, it kind of flips them around. This is the change in potential energy right here. Final minus initial. Final minus initial, that's the change in potential energy. So, again, I can rewrite that now. So change in potential negative, because I pulled out that negative, change in potential energy equals kinetic energy. And now we can actually just plug in the stuff I just showed you all. In the last slide, I told you all that the change in potential energy is, so negative is negative Q E D cosine theta. And the kinetic energy is 1/2 mv squared. Okay? So there's a lot of steps. There's a lot of things, we're doing a bunch of steps here. But again, it's just to show you what is this used for. Again, this is not actually a problem you are going to be solving. It's just to conceptually show you how these things are going to, it is a conservation of energy problem. I'm going to spend a few more moments on this and actually kind of get some kind of final result, because there's some useful things here. But really what I want to show you all today is that if you understood conservation of energy when it came from Physics 1, you can understand what I'm going to teach you all today. Except instead of gravity, now we're working with electric fields and this electrical potential. All right, so the last thing, again, at this point, you know, if I gave you numbers, you could solve it. But the last thing I just want to remind you all is that the electric field for a plane of charge is sigma over epsilon naught. That was an equation I gave you all last week. So then we could plug that in and we could do a bunch of algebra and get the answer. But that's really just the last thing I wanted to point out to you all, is to remind you that if you have a plane of charge, because I specifically chose a plane of charge here because I wanted to remind you all, if you have a plane of charge, it does not matter how far away you are from this plane of charge. So, you know, the negatives cancel, so we get the angle of the electric field and the direction this thing's moving. That's going to cancel out, so we're fine. Equals, oh, did it break on me? We dreamed big dreams that we'd have no technical, oh, there we go. Great, equals 1/2 mv final squared. It simplifies to that. And then again, you can solve for velocity. Well, I'm not going to spend the time doing the algebra. All I wanted you all to see really was this here. That the stuff we're going to talk about today is very similar to what you talked about in Physics 1. One of the big challenges in Physics 2 is we're talking about things you can't see. You can't see charges. You can't see fields. You can't see voltage. So if I can connect it to Physics 1 and stuff that you could see, you can see an object falling. You can kind of understand that gravitational potential. So if you understood that, get your head in that mindset, gravitational potential energy. All right. So, bam, if we do the math and we kind of rearrange things, so this is the equation I gave you all before. We find the potential to that, not a huge deal. I'm not going to bother with it. I'm literally going to skip right past it because I'm not stressed, don't spend the time on it. Bam, these two slides are literally just doing the derivation I just did, okay? It's just nicer writing. So if you didn't like my handwriting, bam, it's in fact, I'm going to erase the star. This is literally just what I just did in typed form. Okay. So, I'm going to hit y'all with this equation that I'm going to show you. If you have two charges, charge 1, charge 2, and you want the energy that system has, this is the equation for it. I'll show you where it came from in just a second. Very, very quickly. So this is something we're going to be using today. This is the energy. So just like if I had the moon and the earth, two things with mass, and I wanted to figure out the potential energy of that system, I'd have an equation for it. You cannot have potential energy stored in a system without two objects. Easy example. You all have potential energy right now, but if you're in space, you wouldn't. The only reason you have potential energy right now is because there's a big old planet below you pulling you down. If the Earth disappeared, you're not going to fall anymore. There is no longer a lower potential energy for you to go to. You have to have two charges, at least, to get a potential energy in the system. Just like in gravity, you had to have two objects with mass to have potential energy. You need you and the Earth. If one of you stopped existing, there would no longer be a potential energy in that system. So this is going to be the same way. Now, how do we get this answer? Again, I'm going to briefly, this is going to be super quick because, surprise, surprise, it involves calculus. There's a reason engineers have to take calculus. It is critical to deriving a lot of equations. It's another toolbox. You don't need to know the derivation. So, the equation was delta U equaled E d cosine theta. So honestly, again, I'm going to kind of very oversimplify this for you all. I have two charges. The electric field, there's a Q here as well. So this is a gross oversimplification. It's not a fancy derivative, but it'll get the job done. The electric field due to 1 point charge is KQ over R squared. We talked about that last week. KQ over R squared is the electric field due to a single point charge. So we just chuck that in here. And you know what? Let's call this one 2. Remember, you need this Q1. This is the one experiencing the field. E2, that's the one making the field. One charge makes the field, one charge experiences the field. Just like the Earth. The Earth makes a gravitational field, you experience a gravitational field, or vice versa. You make a gravitational field, and the Earth experiences your gravitational field. The order does not matter. All right, great. So we chuck these in here. Q, K, Q2 over R squared. This cosine theta is going to go away. This is actually a good point here to pause. D and R are actually the same variable. Distance and radius here. So distance is the distance between the two charges. R is the distance between the two charges. Distance is one of the only variables where we get a bunch of different letters for it. So long story short, this D is R. And if we then just put it all together, that R cancels, that square cancels, bam, we very roughly derived it. That's the energy of a system. And all we did was put the electric field in, and again, technically you have to integrate it, but don't worry about it. All right. So that's our energy of our system. Now, originally this was change in potential energy. So how do we get this equation which just says it is this? How do we just get the equation without a change in it anymore? All right, final minus initial. Let's go ahead and place the final infinitely far away. When r is infinitely far away, if you divide by infinity, it goes to 0. So boom, gone. One of the terms disappeared. All right, again, you don't need to know that too much. What you do need to know is this is the energy stored in a system with 2 charges. Okay, that's what you need to know. After all that shebang, if I have 2 charges and I say, what's the potential energy of that system? You do the math. Okay. So, let's see. Do we want to spend the time on this? Nope, because it's a hidden slide. Have fun if you want to do that yourself. It's solved there. Again, guess what you need to figure this out? Calculus. So guess what we don't have to do? Calculus. So the slides are there if you want to look at them, but obviously you don't need it. All right, great. Look, this thing I already told y'all. This is the main takeaway. It's nice and organized. The potential energy for a system to do work due to electric forces, the variable is U for potential energy, E for due to electric fields. We have to start specifying, so when you all learned about gravity, technically, we'd start putting a G next to it because we have different kinds of potential. Energy is always joules. You got energy due to heat? Joules. Energy due to kinetic energy? Joules. Energy due to spring? Joules. It's all joules. All energy is joules. And yeah, the general form is that, but for 2-point charges. And notice this line right here. So, when you're solving for electric field, the bottom's squared. When you're solving for force, the bottom is squared. In our derivation we just showed, it ends up that squared goes away. So this is one of the most common. Do not forget the squared when you're doing the other ones. And this one, don't square it. It's a very subtle difference. Literally the only difference between this equation and the force equation is that in the force equation it's squared. You have to know what you're solving for in a problem so that you choose the right equation, because if you don't, again, look how subtle that is. Such a tiny difference. And yet, if you make that mistake, you will get the wrong answer because you will solve for force. Now, good news about this. This is not a vector. It's a scalar, which may not mean much to you, but here's the benefit. No components. No x component, no y component. It just is. The potential energy just is a value. Now, that value can be positive. That value can be negative. You'd be like, how can I have... Well, I don't know if you're asking this question, but in gravity, how could I have a negative potential energy? Well, if I set the ground to 0 and I fall in a hole, my height is negative because the hole, I'm below the ground and the ground was 0, so I'm at a negative height. That's a negative potential. Something important that I'm going to repeat throughout this presentation, potential energy is all relative. So when we talk about height, when you all did gravity and you said, one of the questions I asked is, how high up are you right now? And the question is, depends what you're referencing. If you're referencing the floor I'm on right now, my feet I'm 0 meters high. But if you reference the center of the earth, I'm a lot more than 0 meters high. If you reference the floor above us, I'm a negative meters high. Height is all relative, so when we talk about potential, every time we talk about it, it's all relative to something. Now, in this specific case, the 0 is infinitely far away. But it's really important to realize that this energy is relative. This potential energy is relative. It only matters when you have a reference. Okay. So, one of the things we want to do in this class, and I think I've already done it with you all a few times, and we're going to keep doing it, and I can guarantee you there'll be test questions like this. Whenever I give you an equation, something we need to recognize is what happens when I change one of the variables. If this doubles, do I get a bigger energy or a smaller energy? If the distance doubles, do I get a bigger energy or a smaller energy? What happens as things change? This equation, again, is a tool. What happens when I tweak things around? That's going to help. If you understand how the equation works, that's going to help you check your answers. So, here's an example of that. We're going to see this throughout the semester. Throughout the semester, whenever I give you all equation, it's very likely at some point soon after we'll see what happens when you change things. If I have two charges, both positive, what happens to the potential energy if I double the distance between them? So looking at that equation, what variable corresponds to distance? And if I double it, how is that going to affect the energy? And I'll even write the equation for you all in here. Now this R12, I just put that down there. It's a distance between charge 1 and charge 2. So here's charge 1, here's charge 2. That's my distance between them. If it's a subscript, it just is, it's like an adjective. R12 is the distance between 1 and 2. It just describes it. It does not do anything mathematically. All right, we'll go to 120. So 5, 4, 3, 2, 1. All right, so this equation, again, this potential stuff conceptually is harder to understand. Forces made sense, push and pulls. Electric fields, we just made up to explain why the forces happen. Energy is a weird thing. So conceptually, energy is going to be a weird thing. But mathematically, it's so much easier because it's a scalar. There's no squareds. So if we look at this equation and we just double the bottom, so R is my distance. So my distance just becomes twice as big. There's no squared. So if we just pull that out to the front, ta-da, I get half the energy. When we did force, or when we did electric field, the bottom was squared, and so whatever happened to the distance also had to get squared. So great job, everyone. All right. So this is just kind of a fun fact situation. Nothing that you all need to know here. But one of the things we can do with this energy thing is predict. So remember, if you all try to touch a desk, your hand doesn't go through that. We can actually use conservation of energy to also explain this. If you have two things going towards each other, at some point, the energy of the system, they kind of equal out and they can't get any closer. So like if I threw two charges at each other, I'm not going to give you a problem like this. We could figure out how close they'd get before they actually rebounded off each other. So energy can kind of tell us how close they'd get before they rebounded each other. We did not have a problem like that with gravity because they never rebound off each other. Gravity, they always attract. But electric fields are weird and we get that whole repulsion. I guess the example of gravity, and this is again a nice fun fact for you. I don't know if you did this problem. It's an interesting one. How fast do you need to go to escape Earth's gravity? You can do it using conservation of energy. You just basically set mgh equal to 1/2 mv squared and say how far do you need to go. And you can do the same thing with charges, how fast. But again, not a huge deal. Don't stress it. Okay, now this is a good one, and I'll talk through this one. This is just reading a graph. I know this graph is not very large, so I'll read through it and I'll point out the parts that matter. A proton is launched from the origin into an arrangement of charges. The potential energy is shown here. So potential energy, as I go up, I increase my potential energy. And this problem says the proton slows, comes to a stop at x equals 3 millimeters, and then starts to move back towards the origin. What was the proton's initial kinetic energy at the time of the launch? Okay, so this seemed like a weird problem, but I'm going to show you all. It's a really easy problem to solve here. So, just to show you all, the thing starts with 0 potential energy, and then as time goes on, that potential energy increases. At 1 millimeter, it's a weird number, like 0.33 or something. At 2 millimeters, it's like 1.33. At 3 millimeters, it's 3 microjoules, and at 4, it's off the screen. Okay, so this is going to be a weird looking problem, but it's a conceptually good one. I have a graph of potential energy, and yet I am asking you for the kinetic energy. And all we know is that the thing starts at 0 potential, and it comes to stop when it's 3 millimeters away. And on our graph, we have that 3 millimeters here. Okay, so we'll go to 150 on this. We'll go for another 10 seconds. Throw out your guess if you haven't already. Don't spend too long worrying yourself about this one. I'll go to 55. All right, and 5, 4, 3, 2, 1. Okay, so again, this problem, it's conservation of energy. That's the purpose of this problem. My potential energy initial due to an electric field, plus my kinetic energy initial equals my potential energy final due to the electric field plus kinetic energy final. So if we look at our chart, in the beginning, I have no potential energy. At the end, I come to a stop. I have no kinetic energy. So really all this problem is saying is my final potential energy is my initial kinetic energy. Just like, again, when you drop that water balloon off a building, your starting initial energy is the same as your final kinetic energy. Again, really just pushing into your all's head, conservation of energy is necessary to solve physics problems. It is a tool in our toolbox to solve problems that would otherwise be disgusting to solve. There is other ways to solve them, but they would be terrible. And honestly, the math skills would not be you would need math that you do not have access to. Calculus. All right, so there you go. How we do? Did I already pick the right answer there? Nope, there it is. So cool. Initial kinetic energy equals the final potential energy, if things cancel out in this way. All right, so to form a hydrogen atom, a protein is fixed at a point, and an electron is brought from far away to a distance of 0.529 times 10 to the minus 10 meters, the average distance between a proton, electron, and hydrogen atom. How much work is done? So this is number 8 from your all's problem set. All right, so let's draw a pretty picture of this. We have our proton. There it is in all its glory. Now, initially, my electron is really far away. I don't know. I guess I could draw it on. You know what? I'm going to draw it up top here since I have the room. So we'll say it's, here, and the electron's really far away, infinitely far away. But, my thing only goes so far. So it's infinitely far away. It's somewhere way off in the distance. So that's kind of my initial. And then my final is, at some later point, the real cozy. Boop, 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 boop. A distance of 0.529. And again, I'm going to start using my notation. Times 10 to the minus 10 is the same as e to the minus 10 meters. And again, this is real value. This is rough, on average, the distance between an electron and a proton. It's real small. Atoms are real small. Okay, so how much work is done? Let's write down some givens, y'all. Charge of a proton is 1.6 e to the minus 19 coulombs. Charge of an electron is negative 1.6 e to the minus 19 coulombs. My distance, now, you know what? I'm going to just put both variables here. R equals D. Because again, R and distance, they basically end up being the same variable a lot of times. So it can be helpful to remind ourselves that they mean the same thing. 0.529 e to the minus 10 meters. All right. Step 2, we're solving for the work. All right, I want to see if y'all can figure out what equation. Spend some time, see if y'all can figure out what. Step 3 is figure out the equation. So that's our givens. What equation is going to let us find that work? Peruse the ones we've talked about. See if you can land on the one that we're going to use. While you all are perusing, I will save this in case my computer blows up. So what equation relates charges and distances to work? I have 2 charges. How can I find the work done to bring them close to each other. Again, while we're waiting for this thing to save, we got Q1, Q2, R, and we're solving for work. Those are our givens. Okay. So we're going to peruse through the slides and see what we have at our disposal. Something I will do is sometime between today and Thursday, I will post the formula sheet that you will have access to on the test. The reason I will do so is that is also a good place to reference when you're solving problems. That will be all the equations in one big block, and one full sheet of paper. All the equations you will need. And so that can be when you're trying to figure out the step 3, you can kind of hunt through that and see if you can find it, as opposed to maybe having to hunt through your slides. So we kind of peruse through our slides and we say, okay, I'm looking for a W somewhere. I'm looking for a W. Oh, there's a W. So we look at our W and we say, we're not trying to find. Yeah, we're trying to find the work. All right, work is force times distance. That'd be really hard to do because the force changes as the thing gets closer and closer and closer and closer. So if you wanted to use force, you could, but this is going to be shocking to you, I know. Guess what we'd have to do that? Calculus. So we don't want to use that one. Wait, look at this other one. Change in potential energy. Oh, do we have a nice equation for change in potential energy that we showed later? That's not that one. That looks work. That's for the plane of charge. Oh, we do. There it is. There's the equation for potential energy due to two different charges at any R. So, bada bing, bada boom, we're going to put those things together. So we remind ourselves work equals the negative change of potential energy. And then we say we know the potential energy due to two charges, Q1, Q2, over their distance between them. Bam. And we could also write this negative U final minus U initial. Just remember change is fine. Yeah?
Oh, why is it negative?
That's a great question. So why is this thing negative? That comes from the derivation from Physics 1. Work is defined as a change in kinetic energy. So I can actually show that in like a couple seconds. So one of the definitions of work is change in kinetic energy. Why is that? That's more derivation, so I won't bother with that. So work is the change in kinetic energy. And if we use our conservation of energy equation, UI plus KEI equals UF plus KEF. If you just rearrange this problem and get KEF minus KEI, you will find it equals UI minus UF. So you can look through this and kind of try to piece this through. So the change in kinetic energy equals the negative change of potential. So if work equals the change in kinetic energy, work equals the negative change in potential. So that's a good question. But yeah, that's where that negative comes from. It comes from the derivation. All right, so we have our equation. So work is going to equal that. So if we kind of put the pieces together, I'm just going to get rid of this negative by flipping it, just like we see at the top here where it's flipped. Work is UI minus UF. And again, we can kind of do that here. K, Q1, Q2 over R1 to initial. You know what? I'm just going to get rid of those 1 and 2 at this point because it's going to get too messy. R initial minus K Q1 Q2 over R final. Okay? And we know all this. We know Q1 and Q2. That's my two charges. We know my initial position. My initial position, this is going to seem weird. It's infinitely far away. So we're going to see what happens. We're going to do some hand-wavy math here. And then R final is where it ends up, that distance that I gave you on the problem. So we're going to copy and paste all this goodness to the next slide. The cool thing is once you've drawn the picture and once you've written this stuff down, we don't have to read the problem anymore, which is good for your mental health, not to have to figure out all that stuff. So there you go. And I am going to copy and paste the picture. So this is, I guess, the downside of me having it up here. Get all this as well, because we're going to need that picture to piece this together. And it totally doesn't fit. All right, down here it goes. All right. And we'll put some boxes around these things. That's my initial. That's my final. Okay, cool. So step 4, plug and chug, y'all. So work equals K, which is 9E9. You know what? Let's make our life a little easier. Let's make it so we don't have to plug as much in. If they both have the same things, they both have K in common. Actually, you know what? Let's make our life even easier. Our initial is infinite. Now, technically, according to the rules of math, you can't divide by infinity, but let's just pretend infinity is a billion, trillion, million, bajillion. It's a big number. If you plug in your calculator 1 divided by a really big number, you get a really small number. If that bigger number gets big enough, bam, that term goes to 0. Infinite doesn't exist in the world, but really big numbers exist. That's effectively what infinite is. Infinite's just a really, really, really big number. And we can basically say it's so big, if I divide it, it's going to go to 0. So we get our equation here. We get our negative 9E9. Q1 is 1.6 e to the minus 19. Q2 is negative 1.6 e to the minus 19. Divided by 0.529 e to the minus 10. I'm going to give myself some room to actually write the answer. We plug that in your calculator and it spits out a number. The negatives will cancel. Now, when we're talking about work, I'll be honest with you all, I'm not worried about positives and negatives as far as your final answer is concerned. I'll just straight up tell you that. If I say find the work, I will say give me the magnitude of the work. The word magnitude is a very nice thing which basically says take the absolute value of it and don't worry about the negatives. Negatives, when it comes to work, means something. It means what's doing the work. Is it, repelling, pushing, all that jazz? But we can figure that out other ways, and it's not worth the time and energy to clarify positive and negative work. Not for you all. Engineering majors, yes. They get to deal with that fun time. You all, not worried about it. So at the end of the day, we just want it to be a positive number, and we're going to call that good. What I care about is you all recognizing that work is the change in potential energy. That's the key part here. That's what I needed you all to know. And what is the unit for this? We just subtracted energies. Energy is joules, energy finals joules, energy initials joules, joules minus joules is still joules. It's joules everywhere. Everything's joules. Joules, all the energies are joules. Kinetic, potential, thermal. Work is just literally the change in energy. I mean, you can see that here. We literally subtracted energies. Work is the change in energy of the system. I went from no potential energy infinitely far away to some potential energy now that they're close by. Just like if you went infinitely far away from the Earth, your potential energy is 0. Because, you wouldn't experience gravity anymore, which gets a weird idea because you're like, but my height's so big. I should have so much potential energy. But yeah, you wouldn't experience gravity, so anywho. Alright, so there's that, just some math that says that work equals potential energy. Another conservation of energy problem. Pro tip to you all. So I'll read this, and then I'll give you my pro tip. I want to accelerate an electron to the speed of sound by electrostatic force alone. To do so, I devise a way to store as much charge as I'd like at a single fixed point, which will be located 0.56 meters from the electron. How much charge do I need to accumulate to accomplish this goal? If you all ever see a problem with speed or velocity in this class, your mind should immediately go to conservation of energy. That is a rule of thumb for any problem in this class. If you see speed or velocity, it is a conservation of energy problem. Where's that? Speed. Conservation of energy is going to come into play. That is the only tools we have at our disposal in this class to calculate velocity. There's no kinematics, no x final equals x initial plus v initial t plus 1/2 at squared. That's what I just taught my physics 1 class last week. They're loving it. Kinematics is the worst. It's all the math. But it's useful, but it's just so much math. Anyway, so conservation of energy. Cool. So let's draw a picture. I want to accelerate an electron. So boom, there's an electron. How am I going to do so? I need to accumulate a bunch of charge. Now, this is a good review. Should I put a bunch of negative charge next to it or a bunch of positive charge? If I want to shoot this thing away, I need a bunch of negative charge. Build up a whole heck of a ton of it. If you put a positive charge there, your charge, well, it's going to go somewhere, but it's going the wrong direction. All right. So, we'll call this capital Q because it's a lot of it. We'll call this one little q because it's just a little baby electron. All right. And these things are 0.56 meters away from each other. So our givens, we know the charge of an electron. 1.6, technically negative. We'll chuck that negative there. Negative 1.6 e to the minus 19. We know the distance between them. Again, I'm going to put r equals d just so we get used to they're the same thing. And we know we want our final velocity is 343. And we also know our initial velocity is 0. Now, there is one more given that we actually need for this problem, but I'm not going to write it right now. We're going to discover what that given is together. If you can figure it out beforehand, very nice, but together we'll also kind of discover what that last variable is. This is sometimes what happens when you're solving problems. Write down everything you think you have, start solving the problem. If you realize you need something else, you can always go back and add it to your list of givens. You can always kind of think through it, be like, oh, I don't have this. Is there a way for me to get that? And you can kind of brainstorm that and figure that out. It's okay to go back to previous steps. All right, we are solving for capital Q. How much charge do I need to build up? And then how are we going to solve this problem? We are going to copy and paste it to another slide. Boom. This is a conservation of energy problem. So immediately, potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Again, I'm putting little e's next to my potential energy because now there's 2 different types of potential energy. Gravity and electric field. Now, we're really only going to be working with the electric field one. I'm not going to be planning on giving you any problems that have gravity in it as well. But it's just good to clarify. It doesn't hurt. All right, so we look at this equation, and whenever you're doing a conservation of energy problem, if you can simplify, you should simplify. If there's any terms that you're like, will go away. So, potential energy is a little funky, so we won't maybe mess with that one right now. But let's look at kinetic energy. Initially, it ain't moving. So boom, that term goes away. Because V initial, you do not have kinetic energy if you're not moving. Right now, you all don't have kinetic energy. Now, this is where I say, remember, all energy is relative. So the question is, are you moving? And you may be like, well, I'm going to move around like that. But on a grander scale, you're on the Earth, and the Earth is spinning, so you're technically moving. So technically, you have conservation of energy. All reference frame stuff. Don't stress that too much. But you are technically traveling real quick, because the Earth's traveling real quick. Well, again, it's all reference frame. You both aren't traveling, but are traveling. Pick your poison. I don't care. If you want to feel like you're going fast, embrace it. All right. So, potential energy. 2 charges, K, Q1, Q2, over the distance between them squared. And we kind of have what we need to start solving this. Now, we also need to remember that kinetic energy is 1/2 mv squared. And at this point, maybe you're starting to see what that variable is that we need. If not, it'll become clear real quick when I plug these in. So now I'm just going to plug those variables in. So K, Q1, Q2 over R initials Ooh, I put a square. Look, I made a mistake. What's my mistake? I squared it. Told you all, it happens. Be very careful with these things, y'all. I thankfully caught it. But that isn't, it's going to happen to you. You'll put a squared where you're not supposed to, or you'll forget to put a squared where you're not supposed to. How do you avoid this? 1, take your time. 2, when you're writing the equation, so 1, write the equation. Don't just skip to writing in the numbers immediately, because that's one way to kind of make a mistake. Another is when you're writing the equation, have that like formula sheet or something that you're referencing. That can kind of also help you. Remember on the test, you will have that formula sheet to literally copy the equation over. If you're looking at it, it's less likely you're going to write it wrong. Okay, so equals K Q1 Q2 over R final plus 1/2 MV final squared. Okay. So you know what? Actually, I guess you could make the argument that there is 2 givens I did not write down. So we look through this equation. K, we know K. I guess I could write K too, but K is 99. You're going to see that so many times, I'm just going to stop writing that as a given because so K is 99, awesome. We have Q to do electrons, so that'll be that one. And at this point, I guess I could write it a bit. Let me go ahead and write it the way that we're going to do it here. So instead, in Q1, Q2, I'll use QE, capital Q, because that's the 2 charges that, there you go. Q1, Q2, I just changed the label, same thing. Just to match what we have here. So great, we got the charge of an electron. We don't have capital Q, but that's what we're solving for, so that's fine. Initial distance. I didn't necessarily label it here, so I can go back and label that. They start that close together. So cool, okay, we got that, that's fine, that's fine, that's fine. We have this K, same thing, that's fine, that's fine. RF, what is my final location? Okay, well if I want this thing to get as fast as possible, we're going to take that distance as far away as possible. Let them affect each other as long as they possibly can. What's the farthest you can get away from each other? Infinitely far away. So again, we're going to do that little math trick. So RF is going to be infinitely far away because, hey, let's make them push each other as much as they can. How do we make them push each other as much as they can? Let them go forever and ever and ever and ever and ever. And it's very convenient for us because that's going to go away now. Divide by a really big number and it goes away. All right, cool. Keep going. Great. We know what 1/2 is. We know the final velocity. The mass. The mass. We have not written down the mass yet. So the question is, what is my thing that's actually traveling? This big old Q here is stuck in place. So it's never moving. So we don't care about that one. But this one, we do care about. We do care about that one's mass. So we need the mass of an electron. And I'm going to fact check myself. I'm fairly confident off the top of my head that this is 9.11 times 10 to the minus 31 kilograms. I will give this to you all in the formula sheet. I do not expect you to have this memorized. I don't expect you to have any numbers memorized in this class. K will be given on the formula sheet. Epsilon naught given on the formula sheet. Charges, heck, those will be given on the formula sheet. So let's just see. Charge of an electron. It's been a little while since I've used, or mass of an electron. I don't want to be using wrong information. Oh, gosh. 9.11A. Good job, me. I remembered. Never hurts to double check, though. Great. So we got everything we need. Let's do some math, y'all. So step 4, plug and chug, y'all. So 9E9 times 1.6 e to the minus 19 times capital Q over 0.56 equals 1/2 times 9.11 e to the minus 31. It's a very small number. Electrons are really small. The key to solving a physics, like at the end of the day, when we're solving a problem, you should only have one missing variable. If you have more than one missing variable and only one equation, it's impossible. Okay, that's a lot of stuff. Before you do any algebra, simplify. Simplify what you can. Make it so you're not having to write as many numbers. So, what I'm going to do is I'm going to plug in my calculator. 9e, oh, and I didn't even write the whole thing. 9e9. So I'm going to type in 9e9 times 1.6 e to the minus 19 divided by 0.56. Before I start moving things around, I don't want to write the numbers a bunch of times, so let's simplify some things. 2.57 e to the minus 19. Now, when you do simplify, don't lose track of the variable that you're solving for. Don't just throw that capital Q away. Don't forget it exists. You need to keep track of where that capital Q is. That's the whole point of the whole problem, is to solve that. If you lose track of it, you're not going to know the algebra to do, because the end goal of algebra is to solve for this Q. So if you don't write Q again, I don't know how you can't solve for it if it magically disappeared. So that capital Q should be there till the very end. All right, we're going to simplify the right side. 1/2 is the same as 0.5, so 0.5 times 9.11 e to the minus 31 times 343 squared. So the right side is also a crazy number, 5.36 e to the minus 26. And at this point, it's a nice and easy algebra problem. And at any point, if it looks like I flubbed something in my calculator, call me out. You've seen me make enough mistakes, you know I am just as prone to them as you all are. Especially when it comes to putting a bunch of numbers in a calculator. Okay, so you divide both sides by 2.57 e to the minus 19. Boom, that side's gone. Q equals 2.08 e to the minus 17. Don't forget your units. Coulomb. And now I don't say I'm done quite, like, yes, I got the answer. I think about whether my answer makes sense. I double check my math. This is the strategy to solve these problems. So I look at this and say, does it make sense? Okay, so I'm going to kind of go back, double check my math, make certain I put my Q's in the right place, make sure I get rid of it. Yep, 1.6, that's fine. Make sure I plug that in. Double check that this number makes sense given these. I had a negative 31. This negative 26 is roughly similar to that, so that's a good sign. And multiplied by a bigger number, so it did go up, so that's good. Same thing over here. This answer, I had a 9e9. And it looks like, see, I didn't make a math mistake. All right, so I multiplied. So again, this is kind of a good little exercise to see, what did I do here? I literally just wrote it wrong. No one caught me on that. So notice that when going through this, I caught my own mistake, because this is what I would do if I was solving a problem. How did I realize my mistake? I have an e to the minus 19 here. I have a 9 times 10 to the 9. That's a big number. That's a really small number. And yet somehow my order of magnitude stayed to the minus 19. I messed up. When you're multiplying exponents, you're like adding the exponents. So times 10 to the 9 and times 10 to the minus 19, those numbers should add. Negative 19 plus 9 is roughly negative 10. And yeah, when I check this, boop, it should have been e to the minus 9. Had that in my calculator, I just wrote an extra 1 for some reason. Do I know why I wrote that 1? No idea. Sometimes you just make mistakes and you're like, why did I do that? That was a stupid mistake. Welcome to the club. It's filled with every human on earth. All right, so 5.36 e to the minus 26. It's just going to change my order of magnitude by 10, but I'm going to be super careful this time. 2.57 e to the minus 9. Oh, did I? That's funny. So I wrote it wrong, but I actually plugged it in correctly. Look at me go. All right. What good timing. My calculator died of batteries. Pro tip, bring extra batteries to your test. So anyway, I actually got the right answer, because so a good strategy that I did on my calculator is, depending on your calculator, you may be able to go up and actually like steal the numbers that you plugged in before. I did that, so even though I wrote down the wrong number, my calculator had the right one. Anyway, there you go. There's the answer. So great. Okay, figured out that mistake, but finally the answer was all right. Does this make sense? Sure, this is bigger than the charge of an electron, and it shows you how strong charges are. Yeah, did I still mess up something?
Is the charge of the electron supposed to be negative?
Yeah, so that's a great question. Should the charge of an electron be negative? So let's kind of think through what the consequence. Yes, so this is kind of useful. I made all of mine positive, and here we can actually see something. What did we say at the very, very beginning? This Q, should it be positive or negative? Negative. We drew that in our picture. I made mine positive. Now, there's a couple things we could have done here. When you're plugging in charges, you could just realize at the end it should be negative and chuck a negative there, but that also would have actually emerged from the math if I had just put that negative sign there. So when you're getting your final answer, it's good to kind of realize, should it be negative, should it be positive? Just think through the logic of that. Yeah?
What if the final potential energy goes on the first equation when you're...
Yeah, so right here?
No, the top.
Yeah, right here?
Yes.
Yeah, so I wrote it. So that's it right down there, but it ended up canceling out, or it ended up going away because we said at the end, we really want these charges to push each other as much as possible. You know, let's let them push each other infinite distance away. And again, fun fact for you all, this math that we actually did here is the similar math that you would actually do to find the escape velocity from the Earth, except instead of k q1 q2 over r squared, or over r, you would use the equation g m1 m2 over distance squared. Yeah. Googled it. Yep. I will give it to you on the test. Yeah, on the test, I will give you all any constant you need. I mean, I guess in this case, I was fortunate that I had it memorized, but yeah, Googling it was kind of the answer here. All right, so let's just kind of do a quick recap. We got 4 minutes. I'm not going to... So what did we learn today? It's always good to kind of do a recap of... We spent an hour and 20 minutes... I spent an hour and 20 minutes jabbering away. What's the main points? There is a potential energy associated with charges. Just like there's a potential energy